So welcome to the session, Other Topics in Quantum Computing 2. The first speaker today is Miguel Navascués. Navascués. And he's going to tell us about first-order optimality conditions for non-commutative polynomial optimization problems. Please take it away.
Thanks, Eva. Good. This talk is going to revolve around the notion of... I cannot see, sorry, so I'm going to stop here. It's going to revolve around the notion of non-commutative polynomial optimization problems, or NPO. This is a bit complicated, so I'm going to unpack a bit this definition. So these objects here represent Hermitian operator variables. They act on this Hilbert space. There are also state variables. Okay, this psi will represent a quantum state, and also a Hilbert space variable. And these functions, they're not arbitrary. These functions are polynomials. They are Hermitian, meaning that if you evaluate them with Hermitian operators, you get a Hermitian operator. Okay, you put everything together, and then you get an NPO. Okay, so the goal is to minimize the average value of this operator among all tuples of operators, such that these operators are positive semi-definite and these are equal to 0. Understood? Okay, this has applications in non-locality, quantum non-locality, and also in condensed matter systems. There are many problems that you can actually reformulate or cast as an NPO. That's the reason why actually I got interested in this in the first place. Okay, the issue with NPOs is that they're nasty. The way it's written, this problem is untractable because this optimization also involves Hilbert space that can have infinite dimensions. So if I try to parameterize, for example, this operator, I will need infinitely many numbers. So this is an optimization problem with infinitely many variables. You cannot attack it by brute force. So what people do normally is to use this trick. Instead of optimizing our Hilbert spaces, our operators, our states, what you do is to optimize our linear functions defined on the set of polynomials of a number of abstract variables. And the way you construct them is like this. This is the correspondence. Suppose I give you some feasible point of this problem. Then I construct this functional in this way. So whenever I want to know what is the value on this polynomial, I evaluate the polynomial with these operators. I get an operator, and then I evaluate the operator with the state. I get a number. Now, if you think a little bit about this, now we won't have time, right? I mean, so I just tell you. You realize that this function has to satisfy lots of constraints. For example, suppose that you take p equals 1 here. Well, you have here psi of 1, but psi of 1 is equal to the identity, to 1. So what we have is that sigma acting on the one polynomial is equal to 1. Similarly, because of this restriction here, it means that if you apply sigma on any polynomial, that results in multiplying a polynomial with its adjoint, so you get something non-negative. This condition, together with this condition, imply that all these polynomials, when you evaluate them, they should be non-negative too. And this condition implies that all the polynomials of this form, when you evaluate them, they're equal to 0. Okay, so this is a relaxation of the original problem. In principle, it should give you some number that is more than the solution of the problem that you want to calculate. And the problem with this relaxation is that it is not good enough because it's also intractable. In order to optimize or in order to define a function over the set of all polynomials, you need also infinitely many variables. So what you do is to relax it further. And instead of optimizing over functions defined over the set of all possible polynomials, you only optimize over functions defined over polynomials of degree 2k or smaller. And this leads you to a semi-infinite program. That's cool. Now you have a semi-infinite program. You can go to the computer to this, and you can get this number. Now you remind that as you increase the degree of the polynomials that you can handle, right, you should get better and better approximations for this lower bound. And in fact, if some condition is satisfied, it's called the Archimedean condition. It's some condition that essentially promises you boundedness. Then you can prove that the sequence of lower SDP bounds will converge to the solution of this problem. And not only that, they will also converge to the solution of this other problem, the original problem, in which you optimize over Hilbert spaces, over operators, and over states. Good. How do you feel? Good. I just summarized NPO theory in 15 slides. I know that this can be a bit overwhelming, but I have a time issue, no? So, of course, I cannot tell you as much as I would like to, right? I mean, at some point, I want to tell you new results. So this talk is going to, before I tell you what this talk is going to be about, I'm going to make a small digression. This is a normal optimization problem. You want to minimize a function under these constraints. okay, see, if this constraint satisfies something called constraint qualification, then you know that the optimal solution will satisfy these conditions, which are called the KKT conditions, the Karus-Tucker conditions. Essentially, they tell you that the gradient of the objective function evaluated on the optimal point is a linear combination of the gradients of the constraints. And you can choose also this coefficient to be positive. And not only that, you can choose it in such a way that mu I times this constraint here is equal to 0. So what we did in our paper is pretty much the same. We take this problem and then we derive some optimality conditions. This is the theory part. Now, the reason why we got a talk in QIP was that it has also some practical applications. It's not just mathematics. So what we show is that, think of this situation. Suppose that you take this MPO, and then we add these mysterious optimality conditions. What do you get? You get the same, right? I mean, you don't get anything else because this thing is redundant. No? But the surprise is what happens if now you apply the same trick that I told you before. You try to use linear functions, right? I mean, to derive a hierarchy of SDPs. Then what you find is that you get a hierarchy of SDPs, but it converges faster than the hierarchy that you have obtained if you have just taken the original problem. Okay, this is a surprise, right? I mean, and it's an application, and that's the reason why I'm talking to you here and not in a conference on mathematics. Okay, so what is the paper about? What will you find if you try to read the paper? The first thing you will find is a heuristic derivation of the first order optimality conditions. That means that we used some non-rigorous argument in order to get a guess about what those conditions are. We use a non-rigorous argument to get the statement of the theorem that we prove later. Well, after the first round of referee reports, I realized that 2 out of 3 mathematicians, even if you tell them that, they will feel very, very, very nervous, right, whenever they see the word heuristic, okay? So we're going to do something else. We're going to do something different. You're going to fall asleep. 1, 2, 3, you're asleep. Okay, we're all asleep. I'm asleep, he's asleep. This guy is not paying attention, he's asleep too. Good. Okay, so we're all asleep. And we're having a very strange common dream, right? I mean, we're dreaming that we find a piece of paper with a problem and we decide that we want to solve it. Okay, so in this dream, we build a Lagrangian for the problem. The Lagrangian simply consists in taking this objective function and then putting some penalty terms for all violations of the constraints. Now, if you pay attention, this is important, if you pay attention to the constraints, they don't make any sense, really, because here you have an integration over the set of all states, which doesn't make sense in infinite dimensions. Here you have an integration of the set of linear functions that doesn't make sense, right? I mean, mathematical sense. But it's fine, because this is all a dream, okay? Things do not have to make sense. It's fine. Okay, how are we going to get the optimality conditions? We're going to take this Lagrangian, and we're going to make small variations on the optimal solution, and we're going to impose that the result is invariant. Okay, so for example, suppose that you take the optimal operators and keep them the same, but then you make small perturbations on the optimal state. Then you impose that at first order, this thing is equal to 0. Well, after some algebra, you get 2 conditions. And now we wake up. Okay, we just woke up out of a nice sleep. And we find that somebody has written something in our notebook. It's written state optimality conditions, and you can find these 2 conditions. So let's see what they mean. So the first one tells you that if you take the optimal states, the optimal operators, and then you use them to evaluate this polynomial that appears in the objective function, and you compute the commutator with respect to any other operator, if you evaluate the commutator with the optimal state, you will get 0. No matter what you put here, what B is. And the second condition is a bit similar. It tells you that if you construct with whatever operator A, an operator of this form, and you evaluate with the optimal state, you will get something non-negative. Okay? These are 2 mathematically well-defined conditions, so it doesn't matter how we arrive at them. Okay? It could have been a dream, or it could have been a heuristic argument. That doesn't matter. What matters is whether they hold. Okay, this is the part that we had problems to make the mathematicians understand. Okay, the first result of the paper is actually that we saw that they hold. They hold in all MPOs that have a bounded solution, and that includes all Archimedean problems. Good. What are the consequences? Well, if you give me any Archimedean problem, and quantum information theory is full of Archimedean problems, then you can add these 2 conditions. And when you derive an SDP hierarchy with these 2 extra conditions, you will get new SDP constraints. And this will boost the speed of convergence of the hierarchy. And another consequence is that now we have a new tool in MPO. Now we can enforce the constraint that the states over which you're optimizing are ground states of some set of other operators. And this is something that we couldn't do before, right? I mean, this is what you get also from the state optimality conditions. Now you're going to fall asleep. 1, 2, 3. You're asleep. Good. We're again in this strange communal dream. And now this time we take the Lagrangian and we make small perturbations on the optimal operators. And this time we get something. Okay, we woke up. Okay, this time it's a bit more complicated, what we find in our notebook, because apparently there's not just one set of operator optimality conditions, there are 4 sets. They have different strengths. Now, in an ideal world, I would tell you about all of them, right? I mean, but I don't have time, right? I mean, I have to choose, right? I mean, so what I choose is my favorite one, which is norm NCKKT. This is what I'm going to tell you today. So suppose I give you an MPO in functional form. So we say that this MPO satisfies norm NCKKT if for any bounded solution of this MPO, there exist a positive linear functionals, mu I and lambda j plus minus. They act on the set of polynomials of these non-commuting variables, just like this other variable here. We demand them to be compatible with the problem constraints. What this means is that this has to satisfy these restrictions, the same restrictions that we enforce on this other variable. They have to satisfy complementary slackness. Now, what this means is that if you take this function and apply it on this polynomial, you get a 0. They satisfy also this constraint. This is a constraint that involves something that you have to define, the non-commutative gradient, right? But essentially, you're evaluating here polynomials with these linear functions that you have here. And this has to hold for all tuples of polynomials. And perhaps the strangest or people do not really understand why we demand this, right? I mean, is this part? How come that we demand this lambda j to be the difference between 2 positive operators? We do it in order to enforce that this, as a linear function, is bounded. Bounded or normed, okay? That's the reason why we call it norm NCKKT. Well, the cool thing, you can see, no? Norm NCKKT is very similar to KKT conditions. Right? I mean, it's pretty much the same. The only thing is that in the KKT conditions, the Lagrange multipliers, mu I and lambda j, they represent real numbers. Here they represent, Hermitian. They're not real, but they're Hermitian functionals acting on the set of polynomials. And the rest is pretty much the same. Now, the interesting thing and the practical thing about norm NCKKT is that it leads to new SDP constraints. So this is suppose that you give me this problem. This will be the SDP relaxation that I would do. And if you tell me then, in addition, this problem is norm NCKKT, then I can enforce all these constraints. Essentially, I define some SDP variables to model the existence of these functionals, and then I relate them to the original functional here, through these constraints here. Okay, so that was just one of the 4 possible variants of operator optimality conditions. We find in the paper some simple Archimedean problems that separate some of these classes. We didn't find anything that separated these 2 classes, but it doesn't really matter because in practice, because we only know how to enforce generally these constraints on the first 3. I wouldn't know what to do with this, apart from imposing all the SDP constraints that follow from this one. Okay, again, it doesn't really matter, right? I mean, the definitions are not that. I'm not John Barrett. I cannot just come here and give a talk, right? I mean, we just definitions, right? I mean, the important thing about the paper is that we also get results, no? So the important thing is to know when these things, when these conditions hold, when you can apply them. And the first one is really cool, right? I mean, because it holds for all problems. You can always apply it. That's the reason why we define something that is extremely loose. For the other 3, you have to check the problem constraints, okay? So we found some sufficient criteria for each of these things. But again, I don't have time to tell you about those criteria, so I'm going to focus on just one, which is this one. This is the criterion that guarantees that you have norm NCKKT, and not only that all Lagrange multipliers are bounded. This is the best possible scenario, because norm NCKKT is the strongest condition that I know how to enforce with SDP. And if you tell me in addition that all the variables are bounded, then there's no reason why I shouldn't encounter numerical problems or anything like that. It's a really cool condition. Now, I don't really have time to explain you this, but yeah, because again, the time. But what I'm going to do is to compare it with a similar criterion that exists in classical polynomial optimization. This is called the Mangasarian-Fromowitz constraint qualification. And if you satisfy, then you prove that the problem satisfies the KKT conditions, and also that all Lagrange multipliers are bounded. And you can see already that it's pretty much the same flavor, right? Actually, if you get into the detail, you find that what this thing is a non-commutative algebraic generalization of this condition here. And this is surprising. You could say, well, why is this surprising, right? You just took this and then you just make everything a bit more complicated, no? And you get the same result. Well, it's surprising because the proof of this result has nothing to do with the proof of this result. Okay, you try to follow, well, it was very interesting to find out this proof, right? I mean, it's relying on the implicit function theorems that do not exist here. So this proof really, we didn't really learn anything that could help us here. So I think it's still curious, right? I mean, that nonetheless, this is still is satisfying this more general scenario of non-commutative polynomial optimization. And I would say this is the most important theoretical results of the paper. Okay, so let's see how these things work. I took this completely ridiculous problem, okay? This problem is Archimedean because of this constraint here. And if you try to solve it using or approximate it using an SDP relaxation at level 4, you get this value, this lower bound. If you enforce state optimality, you get something slightly better. If you enforce essential NCKKT, which you can, because this problem is Archimedean, you get something slightly better. And if you put both of them, then you get something reasonably better than the previous estimate. Now, reasonable improvement is all we found. I would like to give you some example where there was really a dramatic improvement using this new condition. We didn't find it. Maybe it exists, but we didn't find it. Okay, there are applications. In the paper, you can find applications in condensed matter physics and also in quantum Bell inequalities, but I don't have time. So I'm going to speak about quantum Bell inequalities very briefly. Suppose that I pose you the problem of calculating the maximum value or the minimum value of some Bell function in quantum mechanics. It turns out that this is an MPO and it's also Archimedean. Now, the only problem of this is that all the theory that we developed doesn't really work that much for this problem because we don't know if it satisfies normal strong NCKKT. So what we did was to develop a bit the theory further, and we found that it satisfies something what we call partial strong NCKKT. Doesn't really matter. In the case where you have scenarios with dichotomic outcomes, in which each of the parties can only get two different outcomes, then these new conditions do not just lead to new SDP constraints, but not to new SDP variables. So in principle, you can enforce them almost for free. Whenever you're dealing with an optimization over Bell scenarios in which you have the dichotomic outcomes, you can always have these constraints, right? I mean, and get a better bound. And what happens when you do that is that in most of the cases, you find that you can skip one or two levels of the MPA hierarchy. This is a reasonable improvement. It's not dramatic, okay? Actually, we did find dramatic improvements when you take this tau tending to larger numbers. It seems that you can skip maybe 4 or 5, but at some point you cannot tell because of the precision of the computer. Okay, so in conclusion, what I've told you today is a generalization of first-order optimality conditions for MPO problems that do not have state constraints. They come in two flavors. They are state optimality conditions. Those allow enforcing new relevant constraints in condensed matter physics. And there are also operator optimality conditions. These do not always hold. You have to check some constraint qualifications, and they are different variants of different strength. Now, okay, you won't understand this but I can just say it by word. It will be interesting to get better results or better ways of modeling equality constraints. These are some weak spot of our paper. And the other thing is it will be also interesting to generalize these things to second-order optimality conditions. And well, Igor, Klep, and I discussed it a bit, and we already got something. And if you're not because of this little part here, this little wrinkle here, then we'll be satisfied and put a paper. I'm going to stop here. Thank you very much.
Any questions?
Hi. So if you have like this an optimization problem at the kth level of the hierarchy, and then you add in these optimality conditions, is it generally included in like the k prime level for some larger k prime?
I don't understand the question. So if you no, I don't understand the question. Sorry.
So think of some like a degree 4 NPO, and then you add these optimality conditions that you found. Will this necessarily be included in like degree K for some
no,
like?
No, not at all. No, I don't think so. No, so then you skip 2 or 3 levels, right? I mean, when you do this.
Right, but I mean, if if it converges, and like eventually, for some level, it'll be in there. But like, is there some quantitative relationship?
Quantitative? I don't know. Well, what I mean, maybe if I understand, is that if you enforce these things, you won't get weird things in the hierarchy that the levels. Okay, let's see. If the k plus 1th level satisfies the conditions, right? I mean, so will the kth level, right? I mean, so to speak, right? I mean, if you consider like because everything is about tracing out entries of the matrices. I don't know if this answers your question, or maybe I didn't understand your question.
Well, maybe I'll ask later. Or
Okay.
ask, or I can re-ask it now. Like, I don't know, like if you take the kth level and you add these conditions, is
Yes.
that contained in the 2th kth level?
No, to my knowledge, no.
Okay.
Yeah.
All right.
I had a similar question, so maybe I'm going to follow up. So in principle, it should be contained somewhere, right?
No, I don't think so. I don't see why.
But then it will converge to a wrong solution.
No, but maybe asymptotically you get to this, right? I mean, but yeah.
Oh, yeah, so asymptotically it should be, so that's the only
Asymptotically,
problem.
yes. Yeah, sure. But it doesn't mean that you can find us, yeah.
Sure. Thank you. The strong conditions, how, can you say something about it? Or?
Yes, yeah, I can, well, let's see. Yes. Strong conditions. Yes, okay. The strong conditions are very similar, but now you have to imagine that, I cannot see. Now you have to imagine that all these things are operators, actually. So you're evaluating the polynomials on the optimal operators. And these functions here, they're functions that act on the set of bounded operators of the Hilbert space where you get the solution. Okay, and that's pretty much it. You don't need this condition because you just enforce that this thing is a functional on the whole sister algebra. So it's already normed, and that's pretty much it. And but the only problem is that the only insufficient condition we found for a strong SKKT is that the problem admits a solution in terms of a sum of squares, which is not always the case. There's a question there.
In the very end, you alluded to connections to MPO problems. Can you just reiterate what you were saying in that in condensed matter? In MPO problems, how does this connect to MPO problems?
Well, the whole talk was about MPO problems.
As in,
yeah.
I mean, I had a particular, but that's a very specific. I'll probably ask you after the talk then.
Tell me, I don't know.
No, I need to look at the...
the slide, okay. The last slide, or... Okay. Up. Like here. Here?
Yeah, the Venn diagram...
okay. Yeah, this one.
Right. It's not very clear from here, probably. That's why... Well, I'll probably ask you later. But I was just looking at those, what each of those meant. So that's strong and normed.
Yeah, this represents the set of problems that satisfy each condition. And this is really everything. All problems satisfy this condition, and this is really, really exclusive.
Right. Okay, right. I sort of understand, right.
Okay, let's thank our speaker again. And we will continue with the next speaker in 5 minutes.